All right, this is part 2 of 10.1, and all this information is going to be about bases. We're going to see how bases are similar to acids in some ways, but also different in many ways. So we're going to start with our properties of a base. So bases will taste bitter. Remember that acids taste sour. Some examples of bases that taste bitter would be black coffee, cough syrup. Some teas taste slightly bitter. Dark chocolate can sometimes taste bitter, or the type of cocoa that you cook with is very bitter. Also, if you test as bases with litmus paper, it will take the red litmus paper and it will turn it blue. So you'll see this red litmus paper turn blue if you test it with a base. Bases will also conduct electricity, and when you add them to acids, they will neutralize the acid to produce water and a salt. Your broad definition of a Bronsted-Lowry base is that bases will accept protons. So remember, acids will donate protons, acids donate, and bases will accept. Whatever is left over after the base has accepted, or what is produced when a base accepts a proton is called the conjugate acid. Okay, so we're going to highlight that there, and we're going to talk more about it. So this is what is produced when bases accept protons. So we'll identify the parts down here. We're looking for the thing that's accepting a proton, and that will be our base. That in this case is our water. And what is produced when the base has accepted that proton is called the conjugate acid. Okay, so remember that the substance that accepts the proton as base, the one that donates the proton is acid. All right, so we're going to draw an arrow that shows how products are produced by moving a hydrogen from one reactant to the other, and we're going to focus on the Bronsted-Lowry bases. So let's just look at the two substances to start with. We have NH3 and H2O, and then let's look to see how they changed. We became NH4 and OH. So we're moving a proton from the water to the NH3, and so our accepting substance is our base. That's going to be the NH3. And then what does the base become after it accepted that proton? That is our conjugate acid. All right, now, while we're here, we're going to go ahead and identify the acid and the conjugate base as well. So our acid is our proton donator. That's going to be our water. And what's left over after the proton is donated is called our conjugate base. So you may notice that your conjugates are always on the product side and your original acid and base are on the reactant side. Bases make conjugate acids, acid make conjugate bases. Identify the reactant that is the base and the product that is the conjugate acid. All right, so we're going to go back to blue, take a look at this substance, and then compare them to what they become afterwards. So this is similar to the last video. We have NH2 here, but we become NH3. We have a hydrogen here, and then we have no hydrogen. So we're obviously moving this hydrogen in this direction. So that means that this becomes our base because it's accepting the hydrogen. And then on the other side, the conjugate acid is what is produced after that base accepts a proton. And we'll go ahead and label the acid as this one because it's donating. I'm going to go back to red for acids. It's donating a proton, and then what's left over is called the conjugate base. A more narrow definition for bases is based on how they react with water. So Arrhenius bases will increase the concentration of hydroxides when mixed with water. I'm going to name that the hydroxide. That's what that OH is called. It's a polyatomic ion, and it's going to be very common for that to show up with bases. So if we have LiOH and we add it to water, it's going to break apart to become lithium ion and an hydroxide ion. The O and the H do not break apart from each other because it's a polyatomic ion. This is what makes a substance a base. Show how sodium hydroxide is both a Bronsted-Lowry base and an Arrhenius base. So we'll do our Bronsted-Lowry base first. So we're going to have to show how a proton is being moved. This one's a little bit more complicated. So we have a proton that's going to be moved from my water to my NaOH, because my NaOH is my base. It's going to be accepting. We'll go back and write it in blue so we can keep some sort of pattern here. This is my base. It's going to accept a hydrogen. And when it does that, what's left over is, what is produced is my conjugate acid. So we're going to be producing, hold on a second. There we go. That's our conjugate acid because we're taking that OH and we're adding a hydrogen to it. And then for our acid, we'll go ahead and do our acid. This is our donator acid. And we are producing, or what is left over on the other side is our conjugate base. So this is a little bit more complicated because this is a strong acid. The sodium is just an extra ion that is floating around that doesn't have anything to do with the final products. But keep in mind that we're destroying one water molecule. I'll mark this one out because we're destroying this water molecule by removing a hydrogen, and we're creating that OH. And then we're creating a new water molecule by grabbing that OH and adding a hydrogen to it. Okay, so now we're going to take a look at the Arrhenius definition, which is much more simple. We're just going to show how if we put this in water, it breaks apart to form sodium plus hydroxide. So you can see some of your similar compounds are, there's your hydroxide, there's your sodium. We want to go ahead and add AQ here, AQ, to show that that is in water. And you can see we have our water shown right here as well. Common acids or common bases. Acetone, this is found in nail polish remover. It's also found in some paint thinners and paint strippers. So nail polish remover is really common. Ammonia, these are found in cleaning products, but it's also found in urine. Common substance in households sometimes. Calcium hydroxide and lithium hydroxide, pyridine, sodium hydroxide. These can all be found in different kinds of bleach. So this can be found in bleach. Lithium hydroxide can be found in some soaps. Pyridine, I can't remember a common source of that, but it is a cleaning product of some sort. And sodium hydroxide is also often found in window cleaner. So you'll see kind of a trend here. Usually bases do a pretty good job at cleaning things because they're going to be working with breaking bonds of substances that are causing stains and being able to remove them from materials. All right, naming bases. So bases follow the same rules as polyatomic ions and ionic compounds. You're going to name the cation first, which is always going to be a positive charge, and then you're going to name the anion. Here's a hint, there's only one anion. It's going to be hydroxide. So if the cation is a transition metal, make sure you indicate the charge of the transition metal, and to do that, you need to use Roman numbers. All right, this is joke. I'm going to leave it right there and see if you can figure out what that joke is. So let's write the names of the following bases. So our first one, we're going to name the cation first because it says we name the cation followed by the anion. Our cation is called sodium, and our anion is called hydroxide. Second one, our cation is called magnesium, and our anion is called hydroxide. The third one, our cation is called iron, but this is a transition metal. So we have to indicate its charge. This is going to be a charge of +2. And then we write our hydroxide. Charge of +2 because I need 2 hydroxides to balance out the charge of 1 iron, and every hydroxide has a -1 charge. So if I need 2 hydroxides, therefore the iron must be a +2. Write the formulas for the following. Calcium hydroxide, so calcium, which is a +2, hydroxide, which is a -1. We cross and drop those, we get calcium hydroxide with parentheses around it because we need 2 of those polyatomic ions. Copper 3 hydroxide, copper is a 3+, hydroxide is a -. Cross and drop those values, and we get Cu, and we need 3 hydroxides to balance out that +3 copper. Or not, yeah, that is copper. Ammonium hydroxide, ammonium is a polyatomic ion that has a charge of +1. Hydroxide has a charge of +2, or -1. Cross and drop those, and we just plug all those things together. Ammonium hydroxide. Strong bases, just like strong acids, will dissociate completely. Weak bases, just like weak acids, will partially dissociate. Same situation as the acids. Here are your strong bases. You need to know these strong bases so that you can recognize them and draw out the dissociation reactions using the proper methods. Sodium, potassium, lithium, rubidium, and cesium are the elements that are in the first group of the periodic table. So it's going to be elements that are in that first group that make up strong bases. And then we have 3 elements, calcium, barium, and strontium, and they are located in the second group right about there. Those 3 elements are going to make the other 2, 3, 4, 5. 1, 2, 3, 4, 5. Those are going to make the other strong bases. So we don't have strong bases made of anything else, just sodium, potassium, lithium, rubidium, cesium, and then calcium, barium, and strontium. You have the formulas on the right-hand side. So just like strong acids, strong bases will dissociate completely. So we write a arrow going to the right to show that strontium hydroxide will break down to form strontium and 2 hydroxides. And if I were to draw a diagram of a beaker with strontium hydroxide in it, we would have lots of hydroxides, at least twice as many hydroxides as we have strontiums. But there would not be any strontium hydroxide settling out anywhere. It's all going to be completely dissociated. Weak bases will partially dissociate in water. So here's our example of our weak base. So if I were to draw another beaker of the same of a weak acid, we would have some of these products. We would have some NH4 plus and some OH minus, but we would also have some NH3 kind of floating around in there. So we would have all 3 of these products floating around in that liquid water, because this guy right here has not completely let go of its hydrogens. I'm sorry, that guy has not accepted hydrogens. All right, so which bases have stronger bonds with their hydroxides? Strong bases or weak bases? Justify your answer. Same kind of question that we had before. So our weak bases such as copper hydroxide have stronger bonds to their hydroxide ions, causing them to dissociate partially. And that is the last slide. So I hope that you enjoyed the presentation and the video, and you were able to learn some things about acids and bases. Looking forward to the next video.